Thank you, everyone. This is Ronnie Chaudhary. I'm the director for the Center for Connected Multimodal Mobility, USDOT UTC. Today, I'm very fortunate to welcome Manveen Kaur. I worked with her for several years on connected vehicles and communication networking. Manveen Kaur is a PhD student in the School of Computing at Clemson University. Her research focuses broadly on wireless networks and systems, specifically designing and implementing, as well as evaluating systems and communication methods for emergent Internet of Things. The two primary systems used in her research are connected vehicular networks and unmanned aerial vehicles. She is currently working on a solution that provides efficient system connectivity and data dissemination services for resource-constrained IoT systems running data compute-intensive applications with strict performance requirements. Manveen obtained her MS degree in electrical and computer engineering from the Ohio State University. She worked in the media streaming industry as a systems engineer before joining Clemson University. Welcome, Manveen. Again, we are glad that you're able to talk in our CPS series.
Thank you, Dr. Chaudhary. Good afternoon, everyone. My name is Manveen Kaur, and today I am really excited to talk about my the recent research conducted by our group in collaboration with MIT Lincoln Labs on the design and validation of an information-centric networking, or ICN, enabled hybrid unmanned aerial system. This research was presented at the Milcom conference in December 2021, and I'm using the same slides I presented there. So for today's talk, we will first briefly discuss what an unmanned aerial system, or a UAS, is. We'll discuss its uses and its characteristics that motivate this work. Next, we'll discuss in some detail the Icn Enabled Hybrid Unmanned Aerial System, or IHUAS, which we proposed in this work. And this is a system designed for unmanned aerial systems that is the central contribution of our work here. And then we will look at the experimental setup and the results from our early validation of the system, and finally conclude the talk with a short discussion on the present and the future research which has stemmed from this work. So let's begin with what an unmanned aerial system is. So an unmanned aerial system, or a UAS, is a system that traditionally has comprised a UAV or a drone that can communicate with a remotely located control station. In this figure, I have called it a ground control station, GCS, over a long-range wireless link. Now, this link could be a satellite link, a radio link, or a cellular link. There are many use cases for UASs, one of which is what Dr. Chaudhary was just talking about with the methane detection. But other than that, so commercially, these systems can be used to facilitate drone-based deliveries. So delivery drones that can be guided by a remotely located control station in a data center or in the cloud. Also in agriculture, these systems are used for crop monitoring, and there are many similar environmental use cases. However, one very important use case for these systems is on the battlefield, where UASs can be used to support a range of battlefield missions. So these could include reconnaissance missions where a drone flies over an area to figure out what the map of that area looks like, or looking for a target and searching and tracking for a target. And our work here is specifically focused on UASs on the battlefield. So let's focus our attention on the UAVs that are a part of the UAS. The US Department of Defense classifies UAVs into 5 groups, and this ranges from the devices most limited in capabilities to the most powerful. So it goes from group 1, which is the smallest, to group 5. And the capabilities are in terms of size, flight capabilities, and the operational abilities of these UAVs. And a UAV in a UAS can typically carry one or more sensors as its payload. So this could be a camera sensor for image recording, a LiDAR sensor, or any other distance measurement sensor, or any sensor that serves the purpose that UAV is meant for. And then the ground control station controls the flight plan that the UAV follows. And this is usually known to the UAV at the beginning of the mission. So the work that a UAS does on the battlefield is is called a mission in the kind of a technical space we are concerned with, which is a military space. So typically, UAS's mission involves the UAV conducting some sort of data sensing, for which it would use onboard sensors that are available to it, and then sending the collected data to the ground control station, where that data can be analyzed to support the mission. And as we are talking about battlefield operations, UAS missions are also safety critical, and they have a very strict time bound. Conceptually, the UAS that we are talking about is similar to a connected vehicular system, where each individual vehicle might communicate with a backend station, such as a edge-based backend or a cloud-based backend, and they use this backend station to share data to and to get feedback from that informs their future decisions. So while here we are speaking in terms of a UAS, the system that we are going to describe is can be extrapolated to a vehicular system or any other mobile wireless system that fits the characteristics of a vehicular system as well. So the issue with traditional UAS design that we described, and that's on the figure in this slide, is that the time it takes for the ground control station to communicate with the UAV and the time that it takes for the UAV to send data back to the ground control station over a long distance link is time consuming. And this closed loop between the ground control station and the UAV results in high latency that impacts the completion time for a strictly time-bound mission. So then what are some ways in which we can lower the communication and decision-making latency on the UASs? The most straightforward way would be to reduce the UAV's reliance on the ground control station for all of its decision-making. And so this would involve implementing some decision-making on the UAV itself. Typically, this decision-making requires analyzing and processing substantial amounts of data. So it relies on computationally intensive functions like machine learning algorithms. So there are two implementation alternatives using which UAS can support decision-making on the UAVs. The first is we could provision the UAV in the UAS with a high-performance embedded computer, or a HPC, as shown in figure 1 here. So in this case, the UAV that we have is fitted with a high-performance computer that can do computation. The advantage for such a system would be that the HPC provides the UAV with comprehensive computational capabilities, which enhances its decision-making greatly, and it is capable of taking most of the decisions it would send to a backend. However, this implementation alternative has disadvantages as well. So first, and the most important, is the cost. The HPC is costly, so it cannot be widely deployed for numerous use cases and must be is reserved for specialized cases. It also adds substantially to the size of the UAV. So if you are familiar with a commercially available UAV, the kind that you might see in Best Buy or Amazon or people flying recreationally, that's the size of a Group 1 UAV, which is really small. So such a small UAV cannot support the fitting of a computer on top of it. So since it adds substantially to the size of a UAV, this can organically only be deployed on larger UAVs, and larger UAVs are costlier to begin with, running often in hundreds of thousands of dollars, if not more. And on smaller UAVs, this also results in issues with maneuverability and the risk of detection. And then having a single component for decision making on a UAV also puts us at risk of a single point of failure in the system, not to mention any cyber attacks, because we only have one node doing everything. And if that node gets compromised, then that is not good for our system. The second alternative that we have is by replacing the single UAV in the UAS with a UAV swarm. A UAV swarm is a group of UAVs which are tasked with supporting the mission that can collectively use all of their sensing and compute resources. This is the implementation alternative that we have explored in our work. So the UAV swarm typically uses smaller UAVs, such as those belonging to group 1 or 2, which are, if you imagine, roughly the size of commercially available drones that you might see flying outside. And this system is heterogeneous in nature. What that means is different UAVs might support different types of sensing and compute capabilities. The advantage of replacing a single, possibly large UAV with a UAV swarm is that this is a cost-effective deployment. There's an ease of being able to scale up the system as required by adding more UAVs, and it's easy to maneuver smaller UAVs without detection or to send them into urban settings as compared to a larger UAV that might not be able to travel with ease in such settings. And the disadvantages of this system also are that each of the UAVs has very limited resources on it, and the system overall is subject to many system constraints, as we'll see in a little bit. Our work is motivated by the requirements of the UAV swarm, which are required to support a critical mission as a part of the UAS. So first, equipping the swarm to support missions in a semi-autonomous or autonomous manner that can reduce the frequency of its interaction with the ground control station. The second requirement is that as each UAV individually is resource constrained, allow different UAVs in a swarm to support different sensor types, and then share the sensor data among all UAVs for a more distributed form of data sensing. And similar to this, the UAV swarm must also be able to allow multiple UAVs to conduct data perception and analysis in a coordinated manner. So an example of distributed sensing and analysis would be 2 to 3 camera sensor equipped UAVs in a swarm that are collecting video data, which can then be analyzed by a different group of UAVs within the swarm that have formed a distributed computing environment. And finally, another requirement, the fourth requirement, is to provide data communication methods to the swarm that can operate even in a highly mobile environment. So a highly mobile environment means that drones or UAVs may fly in and out of range of each other. They may have intermittent connectivity, and a network might undergo dynamic reconfiguration as a result of the system's mobility. So we need to have data communication methods that are tolerant of this. So overall, a UAV swarm must be able to communicate with low latency, high reliability in a wireless mobile system to successfully support this set of requirements. And providing such a communication framework with low latency and high reliability is a central objective of my extended work and is the subject of my ongoing research. So these are the main contributions of this work. First, to facilitate low latency and high reliability communication in a UAV swarm, we present a UAV swarm-based UAS design, which we call the Icn Enabled Hybrid Uas, or the IHUAS. Then the IHUAS design, it extends a typical UAV swarm by leveraging a hybrid composition in which we utilize a small number of powerful group 4 or 5, which are the larger UAVs, in addition to smaller group 1 UAVs. And the hybrid composition of our design provides the swarm with ample aggregated compute power to support autonomous decision-making within the swarm. And the swarm still remains flexible because the smaller UAVs can fly in and out while within a wider area, while the larger UAVs stay confined to a smaller region and provide the control component that is more compute intensive. So this system supports scalability, as it is possible to add smaller UAVs as and when required. Having a powerful compute environment in a UAV swarm also allows the swarm to operate without the ground control station. And this is especially helpful in areas where the connectivity to the ground control station might be limited. So even outside of the battlefield, if you imagine drones conducting a disaster management mission where they're trying to find for survivors after a natural disaster, they might not have access to, they might not have good connectivity to a backend. So having this sort of a system, which is sufficient in itself, is really helpful for such cases too. For communication, the IHUAS uses information-centric networking, or ICN, and this is done through publish subscribe message dissemination conducted using brokers. And we will talk about this in some more detail in a little bit. Overall, the system that we are recommending provides low latency and reliable data dissemination that can support a critical mission on the battlefield. The early validation of IHUAS also serves as a performance measurement study of ICN in a mobile wireless environment like a UAV swarm. So ICN has recently gained a lot of interest for its many benefits to mobile systems which are data oriented, but there still exist only very few studies that quantify or compare the use of ICN in such a system compared to more traditional methods like unicast or broadcast or even multicast. So in this work, we also provide a comparison of communication latency and reliability, which is achieved through ICN under various operating conditions, and compare it to standard unicast communication. And within this, we are also exploring configurable ICN parameters, like the number of brokers to use and where to strategically place them, that impact eventually how useful ICN is within this system. And finally, the use case that we are using to illustrate our design and to conduct the measurement study here is that of IHUAS supporting a time-sensitive coordinated search and tracking, or a CSAT mission on the battlefield. And we will talk more about this and more specifics of the public subscribe method in the next section. Okay, so now let's talk about the IHUAS design in a little more detail. So this system is, like we said earlier, heterogeneous in composition. It comprises primarily of small group 1 UAVs, which are resource constrained, but also includes a small number of larger and more capable UAVs as represented in the figure here. The UAV swarm follows a leader-follower model. The leader or there could be a distributed set of leaders, are the larger group 4 or 5 UAVs within the system. We assume that of all the group of group 4 or group 5 UAVs that are available, some nodes are elected as leaders, while other nodes being while other nodes function as backups to the leader. And it is possible for any group 4 or 5 UAV to function as a leader as long as they have the physical hardware to support this role. And in terms of hardware, a leader node or someone capable of being a leader node should have at least 2 communication interfaces, one of which is for communication within the swarm and one for communication with the ground control station using a different type of connection. So that's either a real and a virtual interface, 2 antennas, or an agile radio that can support 2 communication methods. While a swarm can have multiple distributed leaders, like I just said, for simplicity in our early validation, we assume 1 leader and multiple followers. Excuse me. So the follower nodes in the swarm are resource constrained group 1 UAVs. Each UAV is small and it can carry a limited number of sensors as payload. The job of the follower nodes is to conduct data collection for a mission. And the follower nodes only need a single communication interface for communication within the swarm, and their communication with the backend is through their leader node. Communication-wise, within the swarm, we use a short-range wireless connectivity method. In our work, we have used IEEE 802.11a wireless standard. However, any short-range wireless standard should work. And some of the newer things we are experimenting with are millimeter wave and 5G for this communication also. And for routing, we are using routing that is established through suitable link layer routing protocols. In IHUAS, mission is managed in the following way. So it is assigned from the GCS to the swarm leader or leaders, who then assign the mission related sensing and perception tasks to suitable UAVs in the system, and then coordinate the data perception and analysis among the computing UAVs which are doing the data perception and analysis. And finally, depending on whether the mission is being conducted autonomously or semi-autonomously, the leader then sends periodic or one final outcome update to the ground control station. So again, drawing an analogy between vehicular networks and this design, the followers here could very easily be vehicles equipped with maybe a short range communication capability and limited computation and data collection capabilities. So this could be a vehicle with a pluggable onboard unit and a camera sensor, or a vehicle with even a cell phone and a camera sensor that is capable of transmitting any vehicular information. And the leader here could be a smart vehicle which is equipped with more compute capable system. So sort of like imagine a Tesla with its multi-core CPU being a leader node. And in some recent works, even standalone UAVs function as mobile edges that can support vehicular networks. And those can also be leader nodes in a hybrid vehicular UAV system. The communication in IHUAS uses ICN. So ICN is very central to this design. And ICN is a very elaborate, detailed topic in itself, but without going into too much detail about ICN, I'll just say that ICN is considered suitable for dynamic systems where nodes are constantly in motion, and especially for systems where the primary thing that we are exchanging with each other is data. So its approach to message dissemination is data oriented, where nodes do not need to know each other's IP addresses, but instead exchange data using the names given to distinct types of data. There are many implementations of ICN, one of which is the publish subscribe based implementation, and that's the one that we use. The figure that we have on the right illustrates the publish subscribe implementation. So we have three main components in this implementation. There's publishers, subscribers, and brokers. Publishers are the nodes that have data to share, and subscribers are the nodes that are interested in this data. And the communication between publishers and subscribers is facilitated through a broker using topics, which are the data names. So topics are string-based identifiable names that we can assign to the different types of data being exchanged in the system. So this will be clearer when we walk through this example here. So in this figure on this page, UAV3 is the subscriber, which is interested in knowing the GPS location of UAV1. So the corresponding topic, or so the corresponding name that is being assigned to that data is UAV1 / GPS location. On a side note, topics use delimiting characters like the / to increase flexibility in data dissemination and make room for casting a wider net in terms of the data that you want. So back to our example. In our example, first, UAV3 tells the broker that it is interested in receiving any data on this specific topic. So now when UAV1 sends data tagged with this topic, the broker can do a topic lookup, know that UAV3 wanted to get this information and send it to UAV3. And at this point, if you know of the MQTT protocol and any of the existing publish subscribe methods, you might wonder how ICN differs from MQTT protocol using off-the-shelf brokers. And the difference here lies in the underlying mechanism for data forwarding. So in MQTT, while the application uses topics, the underlying forwarding that the broker uses and that the system uses is still IP-based. But in a pure ICN system, our underlying forwarding is independent of IP addressing. And what we are implementing here is a hybrid system where to some extent our forwarding is IP independent, but then there are points in the communication where we're still using IP addresses. At a very high level, some benefits that ICN offers over traditional IP-based communication is first, the overhead in ICN is lesser compared to traditional host-centric IP-based methods. So this helps in conserving our very limited system resources for Group 1 UAVs. Second, this system allows us to decouple senders from receivers. So this lessens any disruptions which are caused from mobility. And third, the broker also provides some form of local data caching that can be used to keep data close to subscribers, reducing the latency in subscribers receiving data, and that can also serve as a repository of recent data. So in case, let's say, UAV1, the publisher in this example, sends to the broker its position or any other information, and then it loses connectivity, then the broker still has access to information which can be shared with other subscribers needing that. This doesn't necessarily apply to GPS location, but maybe other data this is more suitable for. And finally, also of note is the fact that the broker is essentially a software function, and any of the nodes in the UAV swarm are capable of supporting this function. The use case for our work here is the CSAT, Coordinated Search and Tracking Application. The objective of the CSAT mission or application is to find targets on the battlefield using the combined capabilities of the entire UAV swarm. And then the data that the UAVs collect for this purpose in the swarm is video data collected through UAVs that are equipped with onboard camera sensors. This is obviously a time-critical mission where the swarm must be able to accurately pinpoint the location of a target at any time and relay it to the ground control station. So in the IHUAS, the ground control station, the GCS, assigns this task to the swarm leader that then assigns the data fencing tasks to some of its camera sensor equipped UAVs, and then assigns data perception and analysis tasks to some other UAVs. There are certain UAVs designated as brokers within the system and through which the data is disseminated when we're using ICN. And as we said, the broker is a software function, and any of our swarm UAVs are capable of supporting this function. So in a more advanced version of IHUAS that we're working on right now, the broker role can be assigned dynamically in response to system traffic. The figure that we have shown here has an experimental UAV swarm setup that we used for our experiments. So this is a simulated testbed that we created. It has nodes in a grid formation. So we have nodes N1 to N5 as the UAVs that are collecting data for the application. And these are shown in green here. We call them the CSAT followers. And our swarm leader is node N23, which is in yellow. The brokers that can be nodes in the, and that can be any nodes in the system, are in this case shown at N8 and N18 in orange, although we did play around with different locations of the broker, and one of our results talks about it. So these are just two potential broker placements. So we use a simple grid formation of UAVs in our early validation for simplicity, but our newer research focuses on more realistic formations that the UAVs might use. Okay, so let's now quickly look at the experimental methodology before we talk about our early measurement results. So the scenario of interest for our measurement within the CSAT use case is a small group of video sensing CSAT follower nodes. So the camera equipped nodes that are sending videos for the purpose of search and tracking. So a small group of these nodes transmitting video streams to the leader node. For the scenarios that we are considering across the board, node N23 is the leader node. We focus on two measurement metrics: one-way delay, which is the time it takes for the leader to receive a message from the CSAT followers. And here we're looking at both the average and the max one-way delay values, and packet error rate, which is the ratio of messages that do not reach the leader compared to the total messages that are sent by any of the CSAT followers. There are certain control parameters that we tweak to represent various CSAT operating conditions for our experiments. With respect to the CSAT application, we experiment with different message transmission rates, different message sizes, and this corresponds to different video bit rates and different encoding types that can be expected in the transmission of video streams. And then with respect to the swarm attributes, we experiment with where the brokers should be placed, the difference in performance when we increase the number of brokers, and the impact of overall traffic in the system on the performance measured between the CSAT followers and the leaders. And we have conducted our experiments using the Kaur simulation tool. And we have used Icn libraries as additional utilities to set up underlying connectivity. We also use two in-house performance measurement tools that we have developed over time. The first is Perf tool, which we use to measure the performance using standard unicast-based communication and the UDP protocol. So this is what we compared our ICN performance against. And the second is a simple PubSub, which is a stand-in for in-house broker software that we used for measuring the performance using our Icn communication method. So since this work, we have worked further on simple PubSub and developed it even more. So for the purpose of this work, both these tools send traffic at a constant bitrate from the CSAT followers to the leader and allowed us to configure the control parameters we discussed earlier. And all measurement data was collected and analyzed at the leader node. So now finally, let's look at some of the results we saw from the system. First, just to set our theoretical expectations, let's look at this theoretical analysis of performance difference when we use standard unicast transmission versus when we use publish subscribe transmission, which is representative of Icn communication. So we conducted a small theoretical analysis where we compared theoretical one-way delay in both cases in a simple wired system. So we use a wired system so that we don't have to worry about complexities from different wireless methods and their characteristics. However, this analysis is applicable to different wireless schemes as well. So we consider two cases in this analysis. One is one sender and none receivers, and this is shown in figure 1A with results in figure 1B. And then we have n senders and one receiver, which is shown in figure 1B, which is shown in, figure 2A. And for these analyses, we consider the broker being placed at various different locations. So the results from one sender and receivers shown in figure 1B show that our theoretical analysis here shows that overall one-way delay increases as the number of receivers increases. And this is dependent both on the number of hops between the sender and the receiver and the total number of the receivers. And the factor of this growth is greater for unicast transmission, which is shown in blue, and it's right under the dashed line that you see. And so as compared to publish subscribe transmission, this factor of growth is overall greater for unicast transmission. However, for publish subscribe transmission, if we place the broker farthest from the receiver, which is right on the sender, the performance for unicast and publish subscribe is exactly the same. But as we move the broker closer towards the receiver, like to X2 and then X3, as we move it closer to the receivers, the growth in one-way delay as we increase the number of receivers is much slower, as can be seen in the graph. Then for n senders and one receiver, which is equivalent to the experimental cases that we were using with multiple CSAT senders sending to one leader node. Again, one-way delay increases as we increase the number of senders overall. So it increases as a factor of the delay characteristics and the queuing at the intermediate nodes. For unicast, and when the broker is farthest away from the senders, so at the receiver, the one-way delay is comparable, like in the other case we saw. However, as we move the broker closer to the senders, we can expect slower growth in one-way delay as the number of receivers increases. And the growth plateau that we see is from each intermediate node having a finite queuing capacity to hold messages. Okay, so our first experimental result shows the comparison of one-way delay for a CSAT mission as we increase the number of senders from 1 to 3 to 5 CSAT sender nodes in figure 1. So we increase the nodes in green from 1, which is just N3, to 3, in which case it's N2, N3, and N4, and then 5, in which case we are sending from N1, N2, N3, N4, and N5. So figure 1 is the reference experimental setup, and N23 is the leader receiving the messages. And for when we are using ICN, N8 is where we have the broker. The CSAT followers are sending messages of size 500 bytes at a rate of 100 kbps, that's kilobits per second, to the leader. And then we have the 3 experimental cases we talked about. So figure 2 here shows the observations from this experiment. So we see that as we increase the number of receivers, the maximum one-way delay we observe for each case using unicast is greater than the maximum one-way delay we observe using publish subscribe. So for the case when we have 5 senders sending, the difference in the medium maximum one-way delay value between the 2 communication methods is 3.1 milliseconds, which is substantial when you consider low latency applications. And let me take a second here to elaborate on why we look at the max one-way delay value here. So the reasoning is that each node has a very specific, unique vantage point to observe the target. So each node has a camera sensor pointed at the target from a different angle. And for the leader to be able to perceive and analyze all the data from the nodes and accurately pinpoint the target, it must be able to receive the data from each of these nodes within a fixed time. So what we measure here is how long does it take for the last node to, so how long, what is the maximum delay for one message to arrive from each of these nodes? And that is the value that we're observing. So this value is of higher interest to us than average one-way delay. So our second experiment result shows the comparison of one-way delay for a CSAT mission using only ICN. So here we change the position of the broker from N8, which is closer to the senders, to N18, which is farthest from the senders. So figure 1 here again shows the reference experiment setup when we have 5 senders and 1 receiver. The senders here use the same transmission rate as our previous experiment, so we're sending at 100 kbps. However, for this experiment, we played around with different message sizes, and here we are showing results for 2 different message sizes, 500 bytes and 1250 bytes. So when we have smaller message sizes, like 500 bytes, we observe that the broker position, whether it was closer or farther, didn't make much difference to the observed one-way delay. This is shown in the blue and red curves in figure 2. However, as we increase the message size, we see a distinct performance benefit of putting the broker closer to the group of senders. So this is shown in the yellow and purple curves, where the yellow curve shows the broker at N8 and the purple curve shows the broker at N18. So the average one-way delay when the broker is closer to the senders is lower by roughly 2.26 milliseconds. Again, substantial for critical low latency applications. And when you start talking about the 97th percentile value of the average one-way delay, that's even higher at 7.36 milliseconds. A use case for different message sizes here is, imagine an application, instead of sending video streams in message form, it's sending video streams in metadata form. And as the granularity and the amount of information it's collecting increases, its message size grows larger. So our system must be able to deal with variable message sizes. Our final experiment here shows the one-way delay and packet error rate from a CSAT mission when we use one centralized broker versus when we use 2 decentralized brokers. So here we use a higher transmission rate of 300 kbps, which is 3 times what we previously used. And the use case for this is the sender's ability to send better quality videos that require higher transmission rates. So the reference figure again shows the experimental setup, where we first have the centralized broker at node N8 and then decentralized brokers at node N7 and node N9. The results we see here are quite drastic and also what we theoretically expected. So the curve for the centralized broker is shown in red at the far end of the graph. This is drastically higher because at some point, the traffic from the senders overwhelms the single broker and its internal transmission queue. This leads to a constantly full queue at the broker, and a pattern of one-way delay is observed where the delay just keeps increasing and increasing till the queue is full, and then it maintains a very high value at which it plateaus. And meanwhile, in the same setting with two brokers, we can see that the brokers distribute the incoming load and their queues don't get overwhelmed. So even when each of the brokers has higher one-way delay than what we observed at lower transmission rates in our previous experiments, the trade-off between higher video quality and the delay are much more feasible and something that we could still work with. And those are the big results we got from our experiments. So finally, now let me conclude this talk with a summary of our discussion and quickly talk about my future work. So we discussed that the IHUAS design is better supported than traditional UASs to support critical missions in the battlefield. So we also provided a measurement-based initial validation of the system, which also serves as a general validation of ICN in a mobile wireless system for which fewer measurement studies exist. Our theoretical and experimental results show that ICN can be used to achieve lower communication latency compared to unicast-based dissemination in the UAV swarm, and we can further control the latency by optimizing where our brokers are placed. Even further, if we use decentralized brokers, we can use those to offer high reliability and low latency for more data intensive applications like CSAT video streaming at higher bit rates. So, and in my present work, which was future work at the time this paper was presented, we are working on the evolution of the simple IHUAS design. Our objective with what we're working on right now is to create a modular and flexible design that is applicable to any generic mobile wireless ad hoc system that is supporting a data intensive application. The design we are working on incorporates decentralized brokers, and it has abstractions for coordination among brokers and to sort of use these brokers as the communication backbone of the system. We're also, as a part of this work, developing a communication framework that is built on ICN, for which the simple pub/sub tool that I talked about earlier is the basis. And this is applied to the evolved design, and it can support name-based communication in these systems. And finally, one big feature of our communication framework is that we are incorporating intelligence at the brokers so that the brokers can control the underlying system and provide suitable environmental changes, so suitable system environment for a particular application that is running in the system. So this brings me to the end of my talk today. Thank you all for being a great audience, and thank you, Dr. Chaudhary and the organizers of the speaking series for this opportunity to discuss my work. If you have any questions, I'll be happy to answer them now.
Hello, Ms. Manveen.
Hi.
Yes, hi. I mean, I've liked the work. I've liked how these unarmed these drones will be working. It's fine, but as you're working with the military, especially in battlefield, you know, currently we are facing these challenges of cyber attacks. And maybe you have not thought about it, but I was thinking, have you ever thought maybe once the leader get attacked and is down, I mean, maybe I was thinking you may try to devise an algorithm that these drones may be switching in leadership law, so that you may be having multiple readers, and the followers may be the same, but switching multiple readers during cyber attacks, it may be much better, because even if you're working in significant adverse condition, maybe the weather is too bad and the reader got disconnected from others, I think it will be the end of the communication up to there. Have you ever thought of switching the leadership among the drones so that the communication may be continuous, efficient?
Right, so that's a great observation and a great point that you're making. So this having one leader and multiple followers was the first simplistic attempt that we made at conducting early evaluation. This system has the capability of supporting multiple leaders. So like I said, that the system will have multiple group 4 or 5 drones, which can be leaders. In the best case, we would have distributed leaders, which all serve as backups to each other. So if one leader is compromised, other leaders can, assuming that there is a way to detect the attack, they can take over the role of that leader, and that leader can be decommissioned for the time being. So that's the ability for redundancy and for other nodes to take on the leadership role are built into the system. However, it's not been you were right in thinking, it's not been the focus of our work here. So this is something we provide as provision for future work, but we weren't focused so much on security.
Okay, thank you. That's
Thank
it.
you.
Anybody else has any question? That would be all. So thank you, Manveen. Thank you so much for your presentation.
Thank you.